Good evening, guys. How is the audio today? Can you hear me loud and clear? Very good. Great. All right. Once again, stay safe. Stay with your family. We are in the mid of this coronavirus pandemics, so please stay safe. Right? That's very, very important. And your exam has been postponed till October, so you have a lot of time to prepare for exams. And preparations, spend times. If you have any problems, questions, please email me to School of PE. Okay, I would like you guys to have your exam passed one shot. Okay, yesterday we talked about chapter 1, chapter 2, chapter 3. Now we'll be taking chapter 4, and I think we will do chapter 5 and 6 also. Then we'll go over the workshop problem chapter 3, 4, 5, 6. Let's see how the time goes. Okay. So chapter 4 talks about compactions and pavement designs parameters. I would say rather than criteria, the parameter used for designing the pavement. There are flexible pavements, rigid pavements. What type of parameters are used? So first of all, we talk about compactions. In order to prepare the subgrade for your foundations, for your roadway, for your any construction sites, new development, you need to compact the soil so that you will have a good bearing strata. Technically speaking, compactions is, if you think about the phase relationship that we reviewed yesterday, a given soil at the site could consist of soil solid if it is unsaturated, water and air in a given specific volumes, right? So during the compactions, under the actions of mechanical effort, it could be roller, it could be jumping jack, anything from outside, you compact the soil so that the air is pushed out and that particular space is taken care by your soil solid and water. If you understand this concept, then you are done with the compactions. So compaction is performed always on the unsaturated soil. Soil should not be saturated. It should be unsaturated because your compactions mean pushing or squeezing out from the soil matrix the content, the amount of air. Okay. So if you want to define compactions, it is defined as densification of soil by virtue of expelling the air from soil solid, water and air matrix under the mechanical effort such as roller. And compaction is always compared in terms of dry unit weight or dry density, gamma D. As I told you yesterday, it's very important because you will look at the compaction level based upon gamma D. So this gamma D is our mirror. This is a mirror to look at what is the level of compaction. Okay. Again, you can read it here. The reasons that we need to perform compaction is in order to make the substrata, subgrade stronger so that there will not be settlement under your working loads. And as the soils are compacted and it is densified, shear strength will increase. So when it's densified, the relative density increase, shear strength increases. And as the voids come close together on the mechanical effort, it makes water to flow through the pore very, very difficult. And this is the reasons we design our earthen dams, pond liners to contain the contaminated substances based upon this thing. If you compact, soil particle will come closures and the voids created will be very, very small, making the pollutant to flow through it very, very difficult or almost nil. Okay, that's dependent upon your design. Also, as the pores are decreased, so larger pore pressure cannot develop. So if there is a seismic event, under seismic event, it will mitigate or it will reduce the potential of liquefactions. Okay, and the factors that affect compaction level is, as I have to stress, water content or moisture content. Very, very simple thing, but this is very, very powerful materials in our geotechnical engineers. So water content in a given soil sample dictates how you can compact the soil. And type of soil being compacted, whether you are compacting fine grained soil or coarse grained soil. Fine grained soils are the soils which are passing through number 200 sieve, and coarse grained soils are the soils which are not passing or retain on the number 200 sieve. Right? So your fine grained soils are your silt and clay, your coarse grained soils are your sand and gravel. So the type of soils will affect the level of compactions. Okay, and followed by amount of compacting energy. What is the energy being impacted on the compacting soil, which is dictated by the leaf thickness, the thickness of the fill materials, and number of the ruler you rule over that fill materials, and the weight of the rulers. So all of these matters are related to the compacting energy on the fill material. Sometimes the compacted fill is also called engineer fill. Do not confuse. Engineer fill, it has been designed. I would like to compact these soils, let's say the level of 97% to the Proctor value, or the 60% or 90% of the Proctor value, whatever it is, it has been designed. So sometimes the compacted fill is also known as the engineer fill. Then type of compacting equipment. There are different equipment available based upon the type of soils. So you have to choose the appropriate type of compacting equipment for the appropriate type of soil. Example could be, you could have smooth drum roller, sieve foot rollers, pneumatic tire rollers, vibrating static roller. But looking at the particles soil that you need to compact, you will recommend what is suitable. And the speed of applications, obviously, if you drive very fast your rollers on the to be compacted soil layer, then the compactions level will be smaller compared to the one which is compacted with the very slow rollers rolling. Okay, so these are the things you should keep in mind, which will clear your understanding in order to understand what is the compactions of soil. When we talk about the compactions, we are comparing everything in terms of dry unit weight or gamma D. This is a plot showing the relations of different type of soil, such as your well-graded gravel, well-graded sand, low plastic silt, low plastic clay as given here with respect to the moisture content. So depending upon the grain size, because gravel will have a larger grain compared to the sand, silt and clay. Clay will have a very small grain, right? So depending upon the grain size or soil type, the peak value of each curve is called gamma D max. And the corresponding moisture content on the x-axis will give the optimum moisture content, W optimum, right? So if I say as the fine increases, your gamma D max is decreasing, right? The peaks are the gamma D. So gamma D max are decreasing. When the gamma D max are decreasing, then the corresponding moisture content are increasing. Okay? So your job is to understand dry unit weight and moisture contents are inversely proportional. If the dry unit weight gamma D max increases, optimum moisture content will decrease. Or if the optimum moisture content increases, your gamma D max will decrease. So they are inversely proportional. Figure on your right also shows a relations between the gamma D and the moisture content, but in terms of the energy, compacting energy for a given soil. Let's say you have a same soil, all right? Soil is not changing, it's for a particular same soil, and you are using different compacting energy level here. Let's say this curve is for 50 number of blues per layer. Let's say you are compacting this soil in a Proctor mode. Then 50 number of blues per layer, 30 number of blues, 25 and 20. So in that case, depending upon the level of energy being used for the compactions, the higher the energy, you'll have the gamma D max higher. Obviously, corresponding moisture content will be lower. And lower the energy, gamma D max will be lower, but the optimum moisture content will be higher. Again, as the blues or as the energy increases, compacting energy increases, your gamma D max will increase, and corresponding moisture content, optimum moisture content will decrease. So you have to know that always optimum moisture content and corresponding gamma D max are inversely proportional. Okay. You can call it for a 5-point test, yes. There is a 1-point test, 5-point test. Okay. But for your sake, what you have to know is from the Proctor test, you can get gamma D max and corresponding moisture content known as optimum moisture content. And these are your conceptual curve. Okay. Not from actual laboratory value, but the conceptual curve. As I told you, there are different type of compacting equipment. And also in the construction side, your soil could have been different form. It could contain of clay, silt, sand, rock. As I told you yesterday, when you classify the soils under USCS systems, the first letters signifies the major component. So you could have a silt as a major component, clay as a major component, sand as a major component, or gravel or rock as a major component, right? Depending upon that percentage, then you can pick up different equipment, compacting equipment here. If you talk about 100% silt, 100% clay, 100% silt, 100% sand, 100% rock, then the best compacting equipment for the clay is none other than sieve foot roller. So if your ground or your subgrade is made of clay and you need to compact, use the sieve foot roller. Okay, sometime in exams they can give you this as a question. In my time, this was the question. In fact, one of the question was this: what is the suitable compacting equipment to compact the clay? There were sieve foot roller, pneumatic tire roller, gravity rulers, and everything was there. But I know the sieve foot roller is the correct one, and I answered that questions. So sometimes they can do it, but thing here is depending upon the soil type, your ruler to be compacted, the soil changes. Okay, this is what you have to know. Application of compacting equipment by soil type. Depending upon the soil type, your compacting equipment varies. In order to understand the level of compaction in the field, you need to take the same sample from the field and take it to the lab and perform the laboratory test. The test performed in the laboratory for the compaction is called Proctor test. And there are two types of Proctor tests. One is called standard Proctor, the other one is called modified Proctors, and designated as, for the standard Proctor, ASTM D698, for modified Proctors, ASTM D1553. Okay. The basis of this test is what is the energy being impounded when the soil is compacted in the Proctor mode. Under standard Proctors, these are the parameters you will use. You will use 5.5 pound of hammer falling from a height of 1 feet, and you will have 25 number of blues per layer. And for that mole, you will have 3 number of layer. With the 3 number of layer, you will prepare the sample for the standard Proctor test. For the modified Proctors, you will have 10 pound heavier hammer and falling from a height of 1.5 feet, 18 inch, right? Higher than this. So it means your energy impounded is higher, bigger. You will use the same 25 number of blues, even for the modified, but the leaf thickness are smaller. So same mold, but if you have to impound for 5 times, 5 number of layers, then the leaf thickness is higher. In that case, level of compaction in the modified Proctors will be higher than standard Proctors. And you can look at here the theoretical energy here. You will have about 4.5%, 4.5 times for the modified Proctors compared to the standard Proctors. Okay, so you can obtain the gamma D versus moisture content relationship in the lab by performing Proctor test. That could be your standard Proctors or modified Proctors. Okay. What varies in either individual test? You can see the variations here. Weight of the hammer varies, height of the fall of the hammer varies, and the layer thickness varies. Number of layer varies between standard proctor and modified proctors. Okay. Not comparing. What do you mean by not comparing them? What do you want to compare them? Varies mean where? Soil type will vary. If you have a different soil at different locations, soil will vary. And the moisture content could vary depending upon the location. Did I understand you correctly, Roddy? So what was your questions? The variations will be soil type and moisture content. Okay. Whenever you are given a proctored curve, it could be standard proctors or modified proctor. Whenever you receive a proctor curve, you always receive the gamma D max and the corresponding optimum moisture content. In the text, they may not tell you gamma D max is this, optimum moisture content is this. But if you need those values, the proctor curve will give you. Okay. So whenever proctor curve is presented to you in exam, you should know that gamma D max and the corresponding optimum moisture content is also given to you. Okay. Theoretical energy means energy being impounded. Theoretically, this you can relate it to this theoretical energy. Weight of the hammer, height of the drop of the hammer, number of blows per layer, and number of layer, and the volume of the mold remains same. See? Okay. So theoretical energy is this. Actual energy is this. So if you design a different type of proctor models with different hammer and different lift, in that case, what was the energy being impounded, you can calculate by using this equation. That's why it's called theoretical energy. So let's do this example in order to appreciate what the proctor did. So please read it first. Standard proctor tests results are given in the following. Volume of the mold, this is the constant. Volume of the mold for the standard proctor test or modified proctor test is remain the same. Weight of moist soils, total weight is given and corresponding moisture content is given. You are required to find gamma D max and corresponding optimum moisture content. So you can formulate this table in this way, because you need to calculate moist unit weight or total unit weight. If you look at your table number 1, for the table number 1, total unit weight, we did the example yesterday, right? Or moist unit weight is the total weight divided by total volume. So total weight is given here, total volume is given here. You can calculate the moist unit weight. If you want to know these values, it's given in the appendix. You can look at there. And this moisture content is given. Once you know the total unit weight or the moist unit weight, then gamma D will be calculated by total unit weight divided by 1 plus moisture content. This total unit weight you will calculate here, and this moisture content is given here. Therefore, you can calculate the dry unit weight. The dry unit weight for this one, the first one is 95.4, second test 102.2, 104.6 is increasing. Moisture content is also increasing, quite valid, right? But if you go here, moisture content is increasing or your gamma D is decreasing from 104.6, it become 101.8. Even the moisture content increase here, still is decreasing further. So if you plot these values, you can get the proctor curve. Without plotting, looking at these values, we can say the maximum gamma D is 104.6 and the corresponding moisture content is 15. Okay, but if you want to plot it, you could plot it, those values. So when you plot it, your gamma D max is here, which we can say is between 104 and 106, and the moisture content is in between 14 and 16. So we could say maximum dry unit weight is 105 and the corresponding moisture content known as optimum moisture content is 15%. This is how you will determine the gamma D max and optimum moisture content. but in exams they will not ask you to plot the graph. In the exams they will give you the graph. If they want to test you, they will give you the graph, and from the graph you have to interpolate the values to get your answers. Okay, that was the test performed in the lab. Now let's look at the compaction test that is performed in the field. Basically there are three types of tests, or they could test you, or they can question you on three types of tests known as rubber balloon method, sand cone methods, and nuclear density gauge method. Rubber balloon methods designated at ASTM D2167 and sand cone methods designated at ASTM D5956 are as given here. Let's say this is your compacted soil and you need to check the level of compaction of this soil, right? You have a subgrade to be prepared, you brought the rollers, you roll it, and you want to know what is the level of compactions. To check the level of compactions at a construction site, you will dig a hole, small hole there, and you take the weight of the soil taken out of the hole, and you will also determine the moisture content of that soil. Then in case of rubber balloon methods, you will bring the rubber balloons here and put the balloon inside, and the vessel has been calibrated in such a way that you will know the volume of the hole directly. So your job is to know the volume of the hole. In case of sand cone method, this is your jar, filled with the jar sand, uniformly graded sand initially, and fitted with the cone here. And the sand is here when your stopper is closed. Okay, so you will take the weight of the sand plus jar per cones initially. Then once you inverted this cone on this excavated hole, then you will drain the sand from top to bottoms, and whatever sand is lost here, that sand went into this cone as well as in this hole. So the cone amount of sand in the cone in terms of weight or volume will be given by the factory. The factory which produced this sand cone apparatus, they will give you. This is standard, right? Then you can calculate then total of that weight, whatever is lost here. Since this is known, then you can calculate the quantity in this hole, and from there you will calculate the volume of the hole. Again, in this test, your job is to calculate the volume of the hole, because that volume of the hole will give you the gamma D, and you have the gamma D from the field, gamma D from the lab. Then you can compare so that you can tell what is the percentage of compactions in the field. So we can read over here for rubber balloon methods, volume of the hole is known from the calibrated vessels, so you don't have to worry. But for the sand cone methods, the parameters known to you would be the unit weight of the dry sand in the jar, we'll call it gamma sand, and the volume of the cone, it could be given in terms of volumes or weight. It's up to the factory, right? The manufacturers of the sand cone apparatus, they will give you. Then what you can measure is the weight of the jar with sand before the test, original weight of the jar with sand after the test. After the test is finished, final weight, and the total weight of the soil excavated from the hole is known because you can measure it, you can weigh it, and the moisture content also you can determine. With this value, the volume of the hole is determined for the sand cone method is either this or this. If your cone correction factor is given in terms of the weight, you will use this equation. If your cone correction factor is given in terms of the volume, you will use these equations to calculate the volume of the hole. Once the volume of the hole is calculated, then your job is to calculate gamma D, dry unit weight, because in compactions always you use gamma D, right? Gamma D is total unit weight divided by 1 plus moisture content, and total unit weight is the total weight of the soil divided by the total volume of the soil, volume of the hole, then divided by 1 plus moisture content. Then this is the gamma D calculated based upon the field value, and this gamma D of the same soil sample will be determined in the lab. It could be standard Proctor, it could be modified Proctor. And when you compare those gamma D from the field to the gamma D from the lab. That will give you the relative compactions, and your job is to determine what is the relative compaction, because that will give you what is the level of compactions that has been achieved in the field by virtue of using that rollers or whatever methods you are using for compactions. Now, in case of nuclear density, you will put the value of laboratory test, Proctor value. It could be standard Proctor value or modified Proctor in the lab. Then you will use the you'll use these nuclear density gates to get the directly relative compactions, level of compaction will be achieved. So this is a pretty straightforward, non-destructive side, so you don't have to make the hole. However, when you use the nuclear density gauge, one thing you have to keep in mind, and they can ask you these things to you, right? When you use the nuclear density gauge in the winter conditions, when your ground is frozen, then this nuclear density gauge will read the moisture content higher. When the ground is frozen, it will read the moisture content value higher. Once the moisture content value is read higher, then the corresponding dry unit weight will be lower, smaller, because they are inversely proportional, right? So effect of frost is moisture content will be read higher, exaggerated value, and the dry density reading will be read lower. Similarly, you may have to prepare your subgrade materials or your subgrade soils to be compacted, and your soil could be unsuitable soil. So you might have to improve the ground, improve the soil. So if you use lime to improve the ground, that lime will contain hydroxyl ion, OH ion, and H ion for the nuclear density gauge is water molecule, but lime is not water molecule, right? Therefore, if you use a ground, if you are testing nuclear density gauge in a ground where the ground has been improved by using lime, then nuclear density gauge will read higher moisture content, and once the moisture content is read higher, then your dry unit weight, dry density will be read lower. So these are the things you have to know, right? Yes, Luis, more or less the nuke test is standard now, but it used to be sand cone test, lower barren methods in earlier, so it's better to know that also. But I do agree, it is more speedy, right? You would not hold the contractor to hold the job to do your test, because this is very speedy and you can do many tests repetitively. That's why this nuclear density gauge in practice these days. Totally agree. So this is the equations to compare the relative compactions. Relative compaction means you're comparing the level of compactions in the field to the level of compactions to the lab value. And I'm sure you have done it in the construction modules, right? In construction modules, one of the popular chapter is compactions. Yeah, I believe most of you must have done it, use the nuclear density gauge, right? Especially those who are working in the construction side, they need to know, they must have used it. Okay, any questions so far in in reference to the compactions? Yes, what is the quick question? How does sand give us dry density of the soil? Even if a soil, your sand is not dry, you can calculate the gamma D, because you can calculate the total unit area of the soil or sand. Then if the soil is moist, you will divide that total unit area of the sand with the 1 plus moisture content to get the gamma D. Okay, what do you mean by when they have different properties? Different type of sand? Same thing, even if the sand is different type, no problem. If the relative compaction is high, what does that mean? That means high means if the relative compaction is high, means it's good. But if your relative compaction is more than 100%, that means your tested soil and the in the lab and the tested soil in the fields are different. Even if it is sand or even if it is clay, it's perfectly fine, Louis. It don't have to be what you call sand. It could be clay. Main thing is you should know the total unit weight and you should know the moisture content, that water content. Although very simple calculation, very powerful. And this is what we did yesterday in that phase relationship, right? We calculate the total unit weight, and for the given moisture content, we calculate the gamma D. That is true for your sand, that is true for your clay. Application of compaction equipment, can you go back and explain? We will do that one later on. That's a self-explanatory. You can look at there. There are different type of equipment suitable for the different type of soil. Or rather than let me go and look at here. This is the one. This is what Edwin is talking about. You got clay, you got silt, you got sand, you got rock, and these are 100% rock or gravel, 100% sand, 100% silt, 100% clay. For the silt, useful equipment could be seafood rollers, tamping roller, high-speed tamping foot, or two tamping foots, right? But for the clay, there is only one rollers which is useful. That is your seafood roller. For the sands, there are so many type of roller you can use it. For the rock, you could use grit rollers or the tamping foot rollers. So this is what this figure has shown, and this is what you have to understand, Edwin. Okay? Are you good? You have to be quick. When you ask the questions, you should be talking to me very quick also, right? Because you will be holding the whole class. The things, it's question for you may not be a question for others. So when I'm explaining you, please respond me quick. Very good. Thank you very much. Let's move on. Okay. We are limited with time, so we'd like to finish on time. Now we'll go on to the parameter that is useful to design the pavement. There are flexible pavements, there are rigid pavements, right? Flexible pavements, example would be asphalt or bituminous pavement. And your rigid pavements could be the reinforced concrete pavement in front of the bridge or the approach area of the bridge and all this thing. And pavement has to be resting or bearing on the soil, right? The bridge is not bearing on the soil. The abutment of the bridge is bearing on the soil. So the pavement designs I refer here is for the flexible pavement, and the California bearing ratio or CVR value is one of the parameters which is used to design the flexible pavement. A relative description on the CVR test. CVR test, as designated by the ASTM 1883, is an indirect measurement of the subgrade strength of the soil below the pavement. In this case, soil below the flexible pavement, right? Harder the subgrade, higher will be your CVR value. Okay, so for the idealized crossrock, we will say the CVR value is 100, and we'll compare every other soil CVR value with this high quality crossrock having the value of 100, CVR value of 100. Okay, we can determine the CVR value by performing the CVR test. CVR test is performed by using 3-inch square diameter plungers penetrating to the soil mold. Once you prepare the soil specimen in the CVR mold is like your Proctor mold, right? Once you prepare the soil in the CVR mold, then you will immerse the specimen in the water for 24 hours. That will give you the reflections of, let's say, flooding conditions in your highway, right? And after that, you will put the load on the plungers and you'll record the penetration, right? So the CVR is calculated as actual stress, load divided by that 3-inch square, right? Load divided by 3-inch square. Actual stress divided by the standard stress multiplied by 100. It should be in number, whole number multiplied by 100, Okay, so severe value for 0.1 inch penetration is calculated as actual stress required to penetrate 0.1 inch for the soil sample divided by the actual stress required to penetrate 0.1 inch for the idealized crosstalk. For the idealized crosstalk, it will require 1000 psi to penetrate 0.1. But for the soil, it will be smaller than that. Whatever is that, if you know this value, you will get severe value for 0.1 inch penetration. Similarly, for the severe value of 0.2 inch penetrations, standard actual stress levels to penetrate 0.2 inch in the severe mode divided by the standard stress, which is 1500. So value of severe 0.1 should be always greater than value of severe 0.2. If that's the case, you will take value of severe 1 as your severe value to design the flexible pavement. Okay. Now, sometime it may so happens your severe value of 0.2 inch penetration is higher than severe value of 0.1. In that case, you rerun the test. After rerun the test, even if you get severe value of 0.2 inch penetration is higher than severe value of 0.1, then you can take severe value of 0.2 as your design value for the flexible pavement. Okay, you can read it when you have time. The other parameters that is useful to design is called subgrade modulus or modulus of subgrade reactions, K. And this is useful for your rigid pavement or rigid slab. Okay, rigid pavement, rigid slab, or mat foundation, because mat is also a very, very big slab. So the modulus of subgrade reaction K is nothing but the slope of the stress versus deflections. So if you run a subgrade modulus plate load test, the plate, you compact the soil, and on the compacted soil you have 30 inch diameter steel plate, and the steel plate you keep on impounding the load. So load divided by area give you stress. So that will be stress versus deflections. What is the settlement of the plate? You can plot. So the stress versus settlements or deflection of the plate will give you the modulus of subgrade reactions K or subgrade modulus K. And this is used for your designing the subgrade rigid pavements. In regards to flexible pavement and rigid pavements K value, American Concrete Institute has given this plot which relate your California bearing ratio CVR value to the subgrade modulus K value here. Okay, so you can look at here. A belongs to the California bearing ratio in percentage, and C is standard modulus of soil reactions K value in pound per cubic inch when using 30 inch diameter plate. So these values are for 30 inch diameter plates. If you use 12 inch diameter plate, and this is the value for modified modulus of soil reactions K12 for 12 inch. So these are the values. Okay, these values are related to the type of soil being used as your subgrade material. So this is your gravel. Gravel has higher value of CVR, higher value of K value. So if you have a subgrade material as gravel, perfectly fine, you don't have to worry. So followed by the sand. But if you have the subgrade material as a silt or clay, then you have to really judge your engineering judgment here. If you look at here, the hatch rectangles represents natural density, and open rectangle represents your compacted density. Let's say unsuitable soil such as your clay and silt. You can see the natural CVR value of the natural clay or silt could be as low as 3 CVR to maximum 5. Okay. Now, if you perform the compactions, right, then your CVR value could rise as high as from 5 to 15. So this is a tremendous increment. If you look at in terms of the subgrade modulus, at natural states, it could have as low as 75 pound per cubic inch to 125 pound per cubic inch. But if you perform the compactions, it will shoot to the as high as 250 feet, double, right? So compaction is very, very important. That's why we perform compactions of the soil in actual construction site, because that will save you a lot of money. Okay, because you have improved the ground. How you can see it? You can see it because the value of CVR as well as the subgrade modulus K will be increased. If these soils are to be used as a subgrade material for the roadway pavement, your roadway pavement will be very, very strong if the soil is compacted. And these are also your interpolated value, right? So depending upon soil type and all this thing, you can see it here. Other parameter these days are very popular is known as resilient modulus. Again, resilient modulus is a parameter used to design the flexible pavement. Therefore, this resilient modulus is tied to the CVR value. Okay, so this is a empirical equations. So the dimensions on the left hand side is not equal to the dimensions on the right hand side, because CVR is your whole number, right, in percentage, whereas in resilient modulus in PSI, it contains of unit. So when your CVR values are less than or equal to 10, then this relation holds good. Resilient modulus in PSI is equal to 1500 times CVR value. So CVR value is a whole number. Irrespective of the CVR number, ASTO has given these equations. So resilient modulus is equal to these equations. Again, these are your empirical equations. This equation has been derived based upon the actual field data. They had a field data resilient modulus plot with the CVR value, and they came up with this equation of they performed the linear regressions, and they came up with these equations, right? So these are your empirical equations. It's not depend upon any theory. It's not dictated by the theory, right? Neither for elastic theory or plastic theory or limit state theory. It is given based upon the actual value. That's why it's called empirical equations. Your resilient modulus based upon the soil type, from gravel to clay, from coarse grain to fine grain soil, fine grain soil. As the grain size decreases, your resilient modulus values also decreases. So higher the resilient modulus means the soil is your coarse grain soil. Okay. Yes, resilient modulus is 1500 CBR, correct. That's what you saw it here, right? Resilient modulus is in PSI, pound per square inch, and 1500 CBR is in your percentage whole number when your CBR value is less than 10. This is used in that context only. When your CBR value is more than 10, you are better off using these equations. Okay. Yeah, CBR value less than 10 dictates toward the fine grain soil. Your coarse grain soil will have CBR value higher than 10. Correct? If you look at here, 10. If you go here, sand will have CBR value higher than 10. So that 10 indirectly tells you these are for the silt and clay. Okay, very good. Now, other things that you need to know is expensive soil. Your fine grained soil, such as clay, is made of different clay minerals. For our engineering's importance, there are three types of clay minerals known as montmorillonite, elite, and kaolinite. If these clay minerals are present in your clay and you happens to use this clay as a bearing subgrade for your foundations or for anything, and these clay minerals will expand if it come in contact with the water. Your water could come to the foundation soil if there is a breakage of the water main, or if there is a rain, if there is a rise in water table by any means, right? There could be flood. If your soils having the clay minerals come in contact with the water, then your clay soil will expand, right? So that will push your foundations, your roadway, whatever structure above it, it will move up. So you don't want to happen that, right? And meantime, when the temperature is dry, water evaporated, everything will shrink, clay will shrink, so the foundations or roadway will move down. So this moving up and down is not suitable, right? So some of the clay soils get expanded, and the intensity of the expansion is dictated by the clay minerals. So clay with the montmorillonite will expand the most, followed by the clay with illite, and followed by the kyanite minerals. To prevent the settlements or expansion of the soil, ground improvement is needed. Okay, you could improve the ground by using the chemical adhesives. You could add these, such as your lime, cement, gypsums, all these things to the soil to stabilize the soil so that the soil does not swell when it come in contact with the water. Or you could install or construct the moisture barrier so that water cannot penetrate to the clay, which has got clay minerals. Or you will compact in such a way that voids are very, very small and water cannot flow through that voids. Or if your area is small and you have got for enough budget, you could take out those problematic soil and replace with the non-swelling clay soil or non-swelling soil or good engineered soil, right? So these are some techniques that you should know. Another important chapter is that you should know is the frost susceptibility, because your construction site, depending upon the weather, depending upon the season of the area of the locations, your soil could subject to the frost if your ground is frozen. Okay, so now if you need to use the construction material or backfill material at a site, then you will avoid using your backfilling materials or structural fill material if it is a silt, because silts, the voids in the silts are such that capillary reactions is more pronounced in the silt soil compared to other type of soil. Therefore, if you happens to have your structural fill over the water table, then you can draw a lot of water from the water table and bring it in the sill, and when it becomes winter conditions, ground is frozen. When the ground is frozen, water freezes to the ice, and if that silt is bearing your building, the building will be heaved. So to prevent that heaving actions, you have to be careful not to use the silt, right? And the capillary rise in the fine grained soil such as your silt is again given by this equation, which is an empirical equation, not based upon any theory, based upon the field observations they gave up this theory. The capillary rise in your silt of fine sands is given by SC in meters is equal to 0.15 divided by effective particle diameter, right? D10 from the gradation curve in millimeters, right? So these are the things that you should need to know. Jill, is montmorillonite the worst one? Correct, 100% in range. Jill, it has the highest swell potential. Good, yes, that's correct. Oh, you answered there. Okay, now we'll move on to, would it be tested for a residential construction, or is this more of a commercial construction? It's up to you. If your owner want to test it, you need to test it, but you should tell it that if your investigation suggests that the clay has got montmorillonite, or if you suspect it has got montmorillonite, you should test it and give your engineering geotechnical report saying that this soil has got montmorillonite and will swells if it come contact with the water. So our recommendation is to avoid building the construction on this type of soil, or you need the mitigation methods to do the construction on this type of soils. Right, subdivisions will do these tests. Any lab test should do it, Joshua. Okay, soil mechanics lab test should do that. If it is a government, yes, DOT or subdivision will do that. Are the soil enough to cause basement wall? Definitely. depending upon your magnitude. If one side swells, other side doesn't swells. If you have a swell, one side of the wall resting on the swells, which is has got more light and it swells, other side of the wall does not heave, then there is a distortion, right? Differential settlement, differential expansion. So that will put the distortions that will crack your structure above it. So for the structure to remain intact, your foundation should be correct. That's why the foundation is very, very important. Okay, very good. Is there anybody from Texas area here in the class? Or Louisiana? James, what is your impressions? Do you face this kind of problem? Stephanie, James. Yes, I'm sure. Means first the geotechnical report should be citing that, right? This is your thickness of the clay layers and this clay content of this kind of clay minerals, and this has a potential of swell. If you do the constructions on this type of swells, your building will be heaved. Your building will be pushed up. My house has a ton of cracks in the wall. Oh, Stephanie, is your building is 1 story or 2 story? Oklahoma, same, yeah, Oklahoma, Texas. That is where Texas don't have basement. Okay, 1 story. It should be all right, I think, 1 story building. Very good. Anyway, please do what do you call the testing, right? Make sure it's structurally, so you to the structural engineers, structurally make sure your building is sound. Minor cracks may not be a big problem, but if it's you have a shear crack, which is a prominent ones, you should let the structural engineers evaluate their engineering material there. Okay. For me, that 1 story, 2 story should not be a big problem, even if there is thing. I'm talking about high-rise building in New York. We have got like 60, 70, 80 story building, but these buildings are on rock. You studied RQD yesterday, so we're looking at the RQD and designing the bearing capacity for that kind of high-rise building with the deep foundation. Isn't the number best in the south due to the high water table and shallow freeze depth? In the north, they installed basement because they have to go deep anyway to get below the freeze line. Oh yeah, that's pretty good, Matthew. I think you made a good point there. Anyway, we can talk. There's a lot of interesting talks going on. I would like to talk on that, but we have limited time. All right. So let's move on first 5, 6. Then we'll do the workshop problem, and if time left, then we'll go and discuss on this thing. Okay. Now my our topics should be, let's finish 5 and 6 also. So the next is permeability, because soil, as we know yesterday, has got voids or porous. So this is a porous material, so the water can flow through it. Seepage, right? So we'll talk about permeability and seepage. First, in order to understand flow, we should understand the Darcy's law. This is the equations or law we have borrowed from the hydraulics, water resources. And also to know about the energy, we should know the Bernoulli's equations. I'm sure you must have done this thing in your water resources, right? So let's see what is the Darcy's law. Darcy's law states that flow through a pipe, before going to swell, flow through a pipe is equal to the average velocity of water multiplied by the cross-sectional area, and cross-sectional area is perpendicular to the direction of flow. Whichever direction water is flowing, you have to take the area which is orthogonal or 90 degree or perpendicular to the direction of flow. In case of soil, the average velocity of water is equal to coefficient of permeability K multiplied by hydraulic gradient I. For us, this coefficient of permeability K, or sometimes known as hydraulic conductivity of the soil, is determined in the lab, so that shouldn't be a problem. what is problem is, what is this I? Hydraulic gradient I. Hydraulic gradient I is defined as difference in total head between two point of interest divided by the distance between the point of interest. So what is that? So if you look at your water resources theorem, let's say this is your pipe, right? You have a point A here and point B there on this pipe. If you insert a piezometers is a meters which will read the water level at that particular point. If you insert a piezometer here, let's say the water table rises there in the piezometer, and if you insert the piezometer at point B, let's say it rises the water level there, right? Then we know change in total head divided by length between the point of interest, in this case point A and point B, will give you the hydraulic gradient. Hydraulic gradient is right there, delta S divided by L. But what is this delta H? This delta H comprises of total head. At point A, your total head is elevation head, if this is your datum, or a line along which, against which you are measuring the elevations, right? This is your elevation head, and the water level in the piezometers or water table will give you the pressure head. Pressure head plus elevation head will give you the total head at point A, and the pressure elevation head and the pressure head at point B will give you the total head at point B. So total head loss when the water particle is traveling from point A to point B is total head at point A minus total head at point B, which is in this case delta H. Therefore, I is this delta H divided by this L. Okay. So this I, hydraulic gradient I, that is to be used to calculate the quantity of flow is delta H divided by L, and that delta H is this. So in literally we can see that total head is equal to elevation head plus pressure head. In hydraulics, you have got velocity head also, plus V square divided by 2G, right? Velocity head. But in case of soil, velocity is very, very slow, so we'll take it as a 0. So you are left with elevation head and the pressure head. Elevation head is also known as potential energy, and the pressure head is known as your strain energy. Sometime if they use this word, you should know that potential energy means elevation head and strain energy means your pressure head. So if you look at here, let's say there is a ground surface and that ground is made of sand, okay, and we know that that ground has a water table. Let's say here water levels at that ground surface is above the ground surface somewhere here, which is 1 feet in this case, right? If you insert a piezometer at the bottom of that sand or the bottom of that soil, let's say it's made of sand, so at the bottoms and in the piezometer you can see water level has risen here. In that case, you can see the water levels at the bottom of the piezometer inserted at the bottom, and the water level above the sand columns are at the same level. These are in atmospheric conditions, are at the same level. Whenever they are at the same level, there will be no water flowing from up to down or down to up. So your soil is simply saturated, but there is no flow. There is no flow means there is no seepage. So mathematically, how we say there is no seepage, we'll calculate the hydraulic gradient I. So if we calculate total head here and total head here, and difference in total head divided by this length will give you hydraulic gradient I. So to calculate hydraulic gradient I here, total head here is your, if you take the datum here, elevation head is 4 and pressure head is water level above this point, top of the sand column, which is 1. So pressure head is 1. So 4 plus 5 is total head at the top, 5 feet. And at the bottom, so if you put a line here, at the bottoms, your elevation head is 2 and your pressure head is from here to here, right? So from here to here is 3. You look at here, this is elevation is 3. Therefore, at the bottom, elevation head is 2, pressure head is 3. Therefore, total head is 5. So your hydraulic gradient I is delta H, total head at the top minus total head at the bottom, which is 5 minus 5, that is 0, divided by 2. So hydraulic gradient is 0. When you have a hydraulic gradient of 0, that means there is no flow. Your soil is only saturated. Hydrostatic condition. Okay. Let's say you have one example indicating like this. This is your sand column. Water level above the sand column is there. And when you insert the piezometer here, water table rises there. So let's draw a line here again, right? So at the bottom, at the top, so this side is water level, this side is higher than here. So water level will be flowing from higher side to lower side. It means water is flowing from top to bottom. Okay. So let's calculate hydraulic gradient I. To calculate hydraulic gradient I, we need to calculate total head at the top, total head at the bottom. Total head at the top would be your elevation head is 4 and pressure head is 1. So 4 plus 1 is 5. Total head is 5 at the top of the sand column. At the bottoms, your total head is elevation head plus pressure head. Elevation head is 2 and pressure head is 2. From here to here is 2, right? Look at here. So 2 plus 2 is 4. Therefore, hydraulic gradient I is 5 minus 4 divided by from here to here is 2 feet, right? The L is 2 feet, will give you 0.5. Once you know hydraulic gradients is 0.5, then if you want, you can calculate the pressure head at the midpoint. To calculate the pressure head at the midpoint, first calculate the pressure, total head at the midpoint. So total head here is 5, total head here is 4, total head here would be 5 minus hydraulic gradient I 0.5 multiplied by the length from here to here. So that is 5 minus 0.5 and the length is 1, give you 4.5. This is your total head. Now, if you need to calculate pressure head, total head minus elevation head is pressure head, correct? Because total head is elevation head plus pressure head. If you want to calculate the pressure head, you know the elevation head, you know the total head, then pressure head is total head minus elevation head. Elevation head is 3, the midpoint. So that will be 4.5 minus 3 give you 1.5 feet. Okay. So this way you can calculate the pressure head and total head at the midpoint of the sand column or anywhere if there is a seepage flow, and you should know the distance. Okay. How is H equal to for the bottom? You insert the piezometer here and you know that piezometer will increase the pressure head at that point. So in this case it's given, right? From here to here, what is the height? Can you tell me the height? James? Is 2 feet. Therefore your pressure head is 2 feet. Okay. It is from pink line, correct? Okay. So this is how. Let's say this changes to this. You have a sand column here, and above the sand column water level is there. If you insert a piezometer here, and in the piezometers water table rises there, right? So in that case, so in this case, since the water level is higher at the bottoms, which is indicated by the piezometers, and lower compared to the lower at the top, so water should be flowing from bottom to top. So seepage is flowing from bottom to top. Then since there is a seepage flow, you can Syed, stay here. I will talk about the midpoint pressure here again, okay? If you understand this, you will understand the previous also. Stay here with me. So here is flowing from bottom to the top. So total head at the bottom would be elevation head is 2 and your pressure head is from here to here, which is these 3 plus that 1, 3, 4. So total head at the entrance is 2 plus 4, which is 6. At the top, your elevation head is 4, pressure head is 1. Therefore, the total head at the top is 4 plus 1, 5. So hydraulic gradient I is 6 minus 5, and this distance is 2 divided by 2 will give you 0.5. Now, look at the side here. If you want to calculate at the midpoint, okay, at the midpoint, first calculate the total head. Total head would be total head at the bottoms minus hydraulic gradient I multiplied by the distance from here to there. So total head at the bottom is 6 feet. Hydraulic gradient I is 0.5 and the length from here to midpoint is 1. So that 6 minus 0.5 times 1 give you 5.5. Total head at the midpoint is 5.5. You know the total head and you have the equation total head is equal to elevation head plus pressure head. Okay? Elevation head plus pressure head. Now, if you have to calculate pressure head at the midpoint, you have got total head as 5.5 feet, elevation head as 3 feet. Therefore, the pressure head will be total head minus elevation head. So, total head is 5.5 and pressure head is 3. So, 5.5 minus 3 is 2.5. So, pressure head at the midpoint is 2.5. If you understand this concept, you will be in the position to calculate the stability of the dam. The dam subjected to the uplift pressure. You can tell whether dam will fail under the uplift pressure or no if you understand this concept. Okay. Let's take this thing. Now here you will help me, right? You will tell me what to do. I would like to use the graph, let's say, and I would like to plot head. Your head could be total head could be elevation head could be pressure head, and I would like to plot that against the elevation head because these are your elevations, right? All of these are your elevations. So let me plot total head first. If I use here, right, your elevation is 6. When elevation is 6, what is your total head? Can you tell me the total head? Give me the total head. 60. Which one is correct? 6. So I have to follow with 6. Why? Total head is elevation head plus pressure head. At this point, when your elevation is 6, your elevation head is 6, pressure head is 0. Therefore, total head is 6. That means when your elevation is 6, if you want to plot against the total head is 6. The point should be there. Let's say here, when your elevation is 5, what is the total head? Can you give me the total head? Is also 6 because total head is elevation head plus pressure head, which is again 6. So when your elevation is 5, total head is 6. So the point should be here, from here to here. When your elevation is 2, is along this point, right? When your elevation is 2, what is the total head? Can you give me? Three or 5? So it's 3, right? When your elevation is 2, your total head should be 3. Elevation is 2, total head is 3, so it should be here. Why is that? Your elevations at the bottoms is 2 and your pressure head is 1. Therefore, the total head at the bottom is 3. When your elevation is 0 here, what is the total head? Is also 3. Your elevation head is 0, but your pressure head is 3, right? Therefore, total head when your elevation is 0 is also 3. So that means the total head diagram is this. Elevations, well, you are plotting elevation versus elevation, so that should be straight line, inclined straight line. When your elevation is 5, elevation is 5. When your elevation is 2, elevation 2, so you can draw that one. That shouldn't be a problem. But it would be interesting if you can plot the pressure head now. Okay, when your elevation is 6, what is the pressure head? So that's your elevation, right? When your elevation is 6, pressure head is 0. When your elevation is 5, what is the pressure head? Pressure head is 1, right? So when elevation is 6, pressure head is 0. When elevation 5, pressure head is 1. When your elevation is 2, what is the pressure head? Okay. Pressure head is 1 or 3. When your elevation is 2, what is the pressure head? Pressure head is 1, right? Because if you draw a line here, a pink line here, so from here to here is 1. So you means these are your point. So if you draw, you will get this one. So this is how you will know the graph. Now if you want to find at the point A, then which is at the elevation of 3, from the elevation draw the line. That will give you pressure head is equal to 1, elevation head is equal to 3, and the total head is equal to 4. So mathematically it's 1 plus 3 is equal to total head 4. So this is how you will draw the plot. If you want to play with the number, same problem, right? Your elevation and flowing from top to bottom. So at the top, elevation head is 5, pressure head is 1, total head is 6. See? At the bottoms, elevation head is 2, pressure head is 1, total head is 3. So your hydraulic gradient I is 6 minus 3, and between here and here is 3. Divided by 3 is 1. So total head at point A would be 6 minus hydraulic gradient I, 1, multiplied by 2. So from there to point A is 2, right? Give you 4. Therefore the pressure head at point A is 4 minus elevation head is 3. So minus 3 give you 1. So whichever way you do, you will get the same answer. Okay? Any question? Why 2 again? Because point A is 2 feet below top of the sand column, right? Okay, that's your L. All right, the next chapter is sea pace velocity. Flow through the soil known as sea pace. You need to calculate velocity. Then velocity is Ki divided by the porosity. Okay, so Ki is average velocity, sea pace velocity, divided by effective porosity. For your case, effective porosity is taken as the porosity of soil itself. From table number 1, whichever way you calculate the effective porosity N, that itself is the effective porosity. If you know the Boyd ratio, you can calculate the porosity. And in other parameter also, if you look at the table, whatever parameter is defined, based upon that, you could also calculate the porosity. So basically, sea pace velocity is the average velocity divided by your porosity of the soil. So keep this thing in mind. Okay. Now, in order to calculate Q, we need to calculate K, coefficient of hydraulic conductivity or coefficient permeability. And we know there are 2 types of soil: coarse grained soil, sand and gravel; fine grained soil, silt and clay. For the coarse grained soil, sand and gravel, the hydraulic conductivity or coefficient permeability will be higher, usually greater than 10 to the power minus 3 centimeter per second. All the time we calculate centimeter and second. Okay. Sometimes it could be inch per second, but usually internationally we calculate in centimeter per second. To calculate coefficient of permeability for the coarse grained soil, we will solve for these equations. Okay, K is equal to V multiplied by L divided by delta H divided by A divided by T. V is called volume of water that is collected in this jar. So if you look at this test apparatus for the constant head permeability, there are reservoir, top reservoir and lower reservoir, supplying the water to the sample, and this one is draining out of the samples and collecting here, and whatever is collected here is collected in this jar. So the volume of water in this jar is B, and if you insert a piezometer of the sample, the top piezometer less the water level is there, the bottom piezometer's water level is there, the difference between the water level give you the delta H, and the length in these calculations, this L is taken as the distance between these piezometers. Whichever distance between you measure the delta H, that length is your length used here. Okay, so this delta H controls this L. Now, if you look at the example 5.1, a constant head permeability test was performed on a 110 millimeters diameter, 270 millimeter tall fine sand sample in a permeameter similar to the one shown in figure 5.4. The piezometers are spaced 200 millimeter apart and had reading of 1809, 1578 millimeters. The graduated cylinder collected 910 milliliters of water over 25 minutes and 15 seconds. Calculate hydraulic conductivity or coefficient of permeability of this soil in centimeter per second. So all the units need to convert to centimeters and time in second. So let's define the parameter given in this problem. Volume that is collected in the jar is given at 910 milliliters, and this is not centimeter, so you have to convert into centimeter, and we know 1 milliliter is equal to 1 cubic centimeter. Therefore 910 milliliter is 910 cubic centimeters. So this is in centimeter. Very good. Diameter is given 110 millimeters. That means 11 centimeter. 5 by 4 diameter square give you the cross sectional area 95 centimeter square, which is direction, which is perpendicular to the direction of flow, right? Cross sectional area. So if you know the diameters, you can calculate the cross sectional area. L is the distance between the piezometer, not the height of the sample, but the distance between the piezometers. It was 200 millimeter apart, so L is 20, and the head difference and the initials were 1809 millimeters, that is 180.9 centimeters minus 157.8 centimeters give you delta H is equal to 23.1 centimeters. So between these readings, the L was 20 centimeters. Now convert that time, 25 minutes 15 seconds in second, that is 25 multiplied by 60 plus 15 give you 1550 seconds. So if you plug in these equations to calculate hydraulic conductivity of the coarse grained soil, right, it could be your sand, right? In that case you will get 5.5 10 to the minus 3 centimeter per second. Any question? If not, the time now is 8:18. We'll break for 7 minutes. Let's meet 6 minutes now. Let's meet at 8:25. Okay, I'll put it here.